Welcome to This Explainer. Today, we're diving into something we literally all take for granted. We're going to follow the epic, high-stakes journey of a single water molecule. Because when you actually stop and look at the science of how water leaves the Earth, travels miles up into the sky, and comes crashing back down, it's seriously nothing short of a hero's journey. Let's get started.
Now, I want you to just think about this for a second. We look up at the sky all the time, but we rarely pause to think about the absolute paradox floating right above our heads. If you took millions of tons of liquid water and put it in a giant tank down here, the weight would be completely unfathomable. Gravity would demand it stay anchored to the Earth, yet somehow, up in the atmosphere, that exact same weight is just gracefully floating by. How is that physically possible?
Okay, let's dive right into this. Just look at the sheer menace and scale of this storm cloud. This is not some fluffy little cotton ball. This is a massive, incredibly heavy structure suspended straight over the ocean. The amount of energy and physical force required to hold that much water in the sky is staggering. The stakes for our story today are huge, because understanding how this menacing mass stays up, and more importantly, why it eventually falls, is absolutely crucial to understanding life on our planet.
Section 1. Earth's Giant Recycling System. Before we get into the clouds themselves, we really got to look at the big picture. This is Earth's overarching recycling system, and without it, rivers dry up, forests vanish, and life as we know it would simply cease to exist.
So this is the hydrologic cycle, basically Earth's ultimate recycling program. It maps the continuous movement of water across our planet, and it has been running 24/7 for literally billions of years. No pause button. And because Earth essentially has a fixed amount of water that just keeps moving through this cycle, the implications are kind of wild. Like, the water in your coffee cup right now? It might have been frozen in a glacier for thousands of years, or, no joke, it could have once been inside a dinosaur. How crazy is that?
Section 2. The upward journey. All right, so how does our little water molecule actually start this grand adventure? Well, it all begins by defying gravity and making a great escape into the atmosphere.
It all kicks off with the sun. The sun is basically the massive engine powering this whole shebang. As solar energy hits the oceans, lakes, and rivers, it heats up the liquid water. Those molecules start zipping around faster and faster until, boom, they gain enough energy to break free and escape into the air as completely invisible water vapor. That's evaporation. To put that scale into perspective for you, roughly 90% of all the water vapor in our atmosphere comes straight from our oceans.
Now, what's really interesting about this next slide is the secret secondary engine of the water cycle. It's not just open bodies of water doing the heavy lifting. Plants are actively pumping water into the sky too. Their roots absorb water from the dirt, pull it all the way up, and release it as vapor through these tiny microscopic openings in their leaves called stomata. We call this transpiration.
To really grasp the macro-scale impact of transpiration, look no further than the Amazon. A massive forest breathes out an enormous amount of moisture every single day. The Amazon rainforest releases so much water vapor into the air that scientists literally refer to it as a flying river. Think about that. The trees themselves are shaping global weather patterns just by breathing.
So, now our water vapor is airborne. Because warm air is lighter than cold air, it naturally rises. But as it goes up, physics kicks in. The atmospheric pressure drops, the air expands, and crucially, it cools down. And here's the golden rule of the atmosphere. Warm air can hold way more moisture than cold air. Eventually, that rising air hits a specific chilling temperature we call the dew point. That is the exact moment the air simply cannot hold all its invisible moisture anymore.
Section 3. The birth of clouds. Reaching that dew point triggers a complete, magical transformation high in the sky, where our invisible hero finally becomes visible again. But here is a totally fascinating twist. Water vapor can't just turn back into a liquid all on its own. It needs a partner to cling to. We call these tiny, microscopic partners condensation nuclei. Basically, the invisible vapor grabs onto specks of dust, ocean salt, smoke from a fire, pollen, or even volcanic ash. Once the vapor finds a partner, it condenses into microscopic water droplets. Clump millions or billions of those together, and you have a cloud.
Which brings us right back to our opening question, right? Why doesn't that cloud, holding thousands of tons of water, just plummet to the ground? It all comes down to size, just 10 to 20 micrometers wide. They are so unimaginably tiny and light that air resistance totally wins the fight. The continuous upward currents of air in our atmosphere just easily support them, keeping millions of tons of water gracefully suspended in the sky.
Section 4. Gravity takes over. But obviously, what goes up must come down. We're reaching the climax of our journey, where the violent battlefield in the upper atmosphere shifts and gravity finally takes control.
So the crucial point here is figuring out exactly when a floating cloud droplet officially becomes a falling raindrop. Inside the cloud, it is pure chaos. Droplets are swirling around, crashing into each other, merging, and growing larger in a process we call coalescence. As they merge, they get heavier, gravity pulls harder, and air resistance becomes less effective. The exact tipping point? It's the second that droplet becomes simply too heavy for the rising air currents to hold up. At that moment, it falls. Rain has officially begun.
But get this, depending on where this is happening, the beginning of a raindrop might not even be liquid at all. High up in tall storm clouds, the atmosphere is freezing cold. Up there, water vapor freezes straight onto ice crystals, which grow into snowflakes and start to fall. If the air closer to the ground is warm, those snowflakes just melt on the way down and hit us as rain. It's totally wild to think that a warm summer downpour you got caught in probably started as a raging blizzard miles above your head.
And when I say miles above your head, I mean it. The sheer vertical scale of these storm clouds is terrifying. A large cumulonimbus cloud, the kind that brings massive thunderstorms and intense rain, can reach vertical heights of 12 to 18 kilometers. That is a massive, towering column of violently rising air and freezing water just dominating the atmosphere. Let's move to orographic rain and see how this builds when the atmosphere interacts directly with the landscape. Picture a massive moist wind slamming into the side of a large mountain. It literally has nowhere to go but up. As the mountain forces the air higher, it cools incredibly fast, hits that dew point, condenses, and just dumps heavy rain on that side of the mountain. By the time the air crosses over the peak to the other side, it's wrung totally dry like a kitchen sponge. That's exactly why you'll often see a lush green environment on one side of a mountain range and a bone-dry desert on the other.
Section 5. Rain Facts and Myths. Now that we've seen how rain is built and how it falls, let's start our final descent. Let's look at what rain actually does when it reaches our level and bust a few myths while we're at it.
Okay, we've all seen those cartoon drawings of a raindrop, right? The perfect little teardrop, pointed at the top, round at the bottom. Total myth. In reality, small raindrops fall as nearly perfect little spheres. But as they get bigger and fall faster, the air resistance pushing up against them actually flattens their bottoms out. They end up looking way more like tiny hamburger buns. And if they get too big, the air pressure literally just rips them apart before they even hit the dirt.
Let's run through some extreme rain facts by the numbers. Because of that air resistance tearing them apart, the absolute maximum size a raindrop can get is about 6 millimeters across. Depending on their size, they're smacking into the ground at speeds anywhere between 8 and 32 kilometers per hour. And as we discussed, a single thunderstorm cloud is dropping millions of tons of water onto the earth. Yet, this distribution is so incredibly uneven that while a rainforest is flooding, some deserts will wait years without seeing a single measurable drop. And that brings us to our final thought. Through evaporation, transpiration, condensation, and coalescence, the water falls, flows right back to the oceans, and the whole hero's journey starts all over again. Earth recycles nearly the exact same water it has had for billions of years. So what does this all mean for us? Well, the next time you pour yourself a glass of water or feel a raindrop hit your face, I want you to look at it with a sense of total awe. Think about the incredible, gravity-defying, billions of years-long journey that single drop has been on just to keep our planet alive. Are we doing enough to respect and protect a system that delicate? Thanks for joining me on this explainer. Keep wondering, and I'll see you next time.